Hi everyone, welcome to the third installment of the Elementum 3D Bridging the Gap webinar series, Bridging the Gap between 3D Printing and Aluminum. Just a few housekeeping notes before we get started. At the bottom of your screen, you'll see a section for Q&A. Please utilize this section to ask any questions. We'll be answering your questions at the end of the presentation, and we'll do our best to answer as many as we can. Any questions we aren't able to get to will be sent to an expert who will reach out to you directly. Please note that this webinar is being recorded and will be available soon. I'd like to introduce you to today's speakers. Joining us from Elementum 3D, we have Jeremy Iden, Materials Scientist and CTO, and Chloe Johnson, Materials Engineer. From 3D Systems, we have Aaron Schmidt, Process and Validation Engineer, and Dustin Krause, Senior Application Development Engineer. At this time, I'd like to hand it over to Jeremy to get us started.
Thank you, Aubrey. So I'm speaking on behalf of Elementum 3D, where I'm the CTO and material scientist. Our mission at Elementum 3D is to expand the material selection and capabilities of additive manufacturing and lead in high-performance AM materials. Our facilities and equipment are located in Erie, Colorado. We have a headquarters and a second facility 2 miles away there, and we're focused on supplying material feedstocks for the additive manufacturing industry. Moving into aluminum, starting with a little bit of background on the naming and so on, because there is some controversy here. Aluminum was named by British chemist Sir Humphrey Davy when he discovered and named it in 1812, when he published his book on chemical philosophy. Some others criticized this name as not sounding classical enough and suggested aluminium. Webster's Dictionary and Alcoa use the name aluminum, which popularized its name in North America, while most of the rest of the world uses aluminium. The oxide remains known worldwide as alumina and not alumina. There doesn't seem to have been the same controversy surrounding the names of platinum, molybdenum, or tantalum. So throughout this webinar, I will use the aluminum name, not aluminium. So why aluminum? Why would you want to use this metal? It has a number of characteristics that make it an attractive choice for AM applications. It's lightweight at about 2.7 grams per cubic centimeter, has high thermal conductivity, one of the highest metals. It's economical with fast print speeds, relatively low material cost per volume. It has good corrosion resistance and good specific mechanical properties. So aluminum and additive manufacturing. There's a lot of different additive manufacturing processes, and they can broadly be characterized as either using a fusion-based process or a sintering-based process. Sintering of aluminum is difficult due to the stable compact oxide layer that forms on the surface of the powder. Sintering typically requires high purity nitrogen environment and a secondary way of overcoming that oxide shell with additives or liquid phase sintering. So we're going to focus on fusion-based processes, which are more widely used for aluminum alloys, but they still have challenges related to the solidification from liquid phase. Fusion-based processes include laser powder bed fusion, DED, including powder and wire DED, and material jetting approaches. So what are these solidification process or challenges that I had mentioned? Well, many aluminum alloys are susceptible to hot tearing, which is a form of solidification cracking. You can see there in the large image on the center, this is a printed horizontal tensile bar, and you can see that there's very large columnar grains present. These grains can grow from layer to layer and continue to grow in the growth direction of the print and become millimeter scale. And you can get brittle fracture and cracking between the intergranular cracking there. On the upper right image, you can see an overhead view looking down in the Z direction of these columns, getting an idea of the width of the column scale. And in the bottom right view, that's an EBSD image in an SEM microscope showing the texture and the grain of the grains that you can see along with the cracking present and defects. So this is a common problem in high-strength aluminum alloys. So there are alloys that have been designed to solve this, and we'll talk about some of those solutions here. So talking about solidification and nucleation in aluminum alloys. Alloy solidification involves nucleation and growth of crystals from the liquid phase to produce microstructures which determine the physical and mechanical properties. Homogeneous nucleation occurs when a crystal nucleates directly from the liquid, while heterogeneous nucleation occurs when a crystal nucleates on a surface. Alloys often have liquidus and solidus temperatures, and in between these temperatures, known as the mushy zone, the equilibrium material is partially liquid and partially solid. During solidification, partitioning of solute elements into the liquid phase can occur, resulting in local compositional changes and constitutional supercooling ahead of the crystal growth. Solidification and cooling also results in volumetric shrinkage in aluminum. And these kind of phenomena can result in solidification cracking in between the dendrites. Solidification morphology can lead to hot tearing, and this limits the printability of many aluminum alloys, including most of the well-known high-strength wrought aluminum alloys. Looking at the figure on the left there, that shows that the solidification morphology depends on the temperature gradient and the growth rate. And based on the gradient and growth rate, both of which can be extreme, especially the gradient in powder bed fusion additive manufacturing, you can get anywhere from planar to cellular to columnar dendritic to equiaxed dendritic microstructures. Especially with the cellular and columnar dendritic, that's where you can have problems with intergranular cracking. Looking at the figure on the right, you can see this is one of the hot tearing mechanisms where dendritic growth results in insufficient liquid feeding in between those growing dendrites, and therefore combined with extensive solute partitioning, and this can lead to the cracking. So microstructural control in AM, you can control the columnar to equiax transition region, and by controlling this, you can control the microstructure that develops. Looking at the figure on the left, you can see that by modifying the alloy, you can shift the curve of how it transitions from a columnar type growth to an equiax type growth. There's many ways to do this, including compositional changes in the alloy. And one way that can actually have the biggest effect within a similar alloy system is to actually add inoculant sites. These are secondary phase, which can facilitate heterogeneous nucleation off of that phase. And so looking at the grain morphology on the right associated with the figure on the left, you can see for alloy 1, which is that dashed line hockey stick towards the left of the chart, you can see you get mostly columnar growth, and then that results in a continuously larger columnar grains that grow from layer to layer with the remelt. For alloy number 2 with parameter 2, or alloy number 2 with parameter 1, for both of those, you'll get a mixed microstructure with a repeated columnar to equiax transitioning and columnar grains of consistent size. So that's an acceptable microstructure, but it's not fully equiaxed. There will still be some directional properties. Or for alloy 2 with parameter 2, you can see you actually get a fully equiaxed microstructure. That leads to more consistent properties and complete elimination of the hot tearing problems. So talking a little bit more about homogeneous versus heterogeneous nucleation. Homogeneous nucleation, nucleation in general, is based on Gibbs free energy. You want to minimize Gibbs free energy for thermodynamic driving forces is in minimizing the Gibbs free energy. And with homogeneous nucleation, there's a larger barrier where the nucleants or the embryos are too small to be thermodynamically stable because the surface area is so large. Generally, when a phase transition is occurring, if it's a favorable transition, the volume of that new phase is thermodynamically favorable, but the surface area, the surface interfacial energy is unfavorable. And so as you grow those nucleants, you reach a stage where the volume to surface area ratio is high enough that those nucleants become thermodynamically stable. And so the energy barrier that needs to be overcome to achieve that is lower when you're talking heterogeneous inoculation sites. And you can see that in the bottom left figure, where the solid phase is forming onto a surface. So this is a way to lower the energy requirements and to promote nucleation by lowering the barrier. So one of the ways that Elementum is focused on overcoming this challenge is through use of reactive additive manufacturing. This is our patented technology that uses exothermic chemical reactions to form product phases in situ during the additive manufacturing process. So it's using precursor phases that in the melt pool will form product phases. RAM technology is used to synthesize target phases for nucleation and dispersion strengthening. You get both benefits. And the RAM additions can solve the hot tearing problems and solidification cracking problems that we just talked about to help make previously unprintable materials printable with properties that match or exceed the properties of comparable wrought alloys. And in the figure on the right, you can see that the precursors can be standard micron type size powders. So you don't have issues that might arise from using nanoscale particulates added into the feedstock. There's none of that. It's all micron scale standard size powders. But in the product phases, you are forming sub-micron size precipitates. So on the order of, anywhere from tens to hundreds of nanometers. This is reaction synthesis inspired. And there's a little bit of an overview on how the thermodynamic calculations are done here. So you're really looking at the enthalpy of the reaction plus the heat capacity over the temperature range with the phase change enthalpy as well. And so these combined allow you to predict the energy released from the reaction and the resultant temperature increase. An example of this is you have constituent A plus constituent B plus the bulk phase might go to form product phase AB with the bulk phase still present. And I have a little video here, so hopefully this plays okay for everyone. And this is an example of a self-propagating high temperature synthesis reaction. So you can see that it was ignited from the bottom using an electroresistive coil. And you can see the energy from the reaction is actually sufficient in this case to propagate the wave up through the pellet, forming the product phase. So the energy released ignites the adjacent layer and it propagates in a continuous fashion. Of course, in additive manufacturing, we're using much lower energy, so there's no risk of propagation. So what does this reactive additive manufacturing approach do for grain refinement and solving solidification cracking? You can see on the left, just an overview, these are EBSD images showing the grain structures of resultant alloys. On the left is a 6061 alloy based on the wrought composition with no modification. And you can see that when printed with laser powder bed fusion AM, you get these very long columnar grains in the growth direction, and you get intergranular cracking. So this type of an alloy would not really be suitable for making real AM parts because of the lack of strength in the cracking present. Adding in a nominal 0.5 volume percent of our RAM inoculants, RAM forming inoculants, you can see that the grain structure is significantly refined, but there is still some directionality to it. Moving to a RAM 1, most of that is eliminated, and you have a very fine grain structure with an average cross-sectional grain diameter on the order of 3 microns. Moving to a RAM 2, which is one of our standardized formulations, you have a grain diameter now of about just under 2 microns and a very equiaxed microstructure, very fine-grained equiaxed microstructure. Moving all the way up to a RAM 10, you can see that there's a little bit further refinement, but not very much. And you're mostly benefiting from the dispersion strengthening in those higher RAM alloys. Looking at the powder, you can see that the powder actually does have multiple discrete constituents in it. This is an example of a backscatter SEM image showing an example of a 2 nominal volume percent RAM alloy. And then on the right, that's the printed product phase. So you can see that In the powder, you do have micron scale inoculants, but in the printed part, you can see that those now are sub-micron size. With that scale bar being 2 microns, you can see that those precipitates are much smaller than that, many of them on the order of a couple hundred nanometers. And this here again is showing the EBSD microstructure with single track rasters. And so you can see the max melt pool depth is approximately in that image there, the second image. And then looking at the right, with the RAM 2 on the left, and you can see it's a very stable, refined microstructure.
Thank you, Jeremy. So yeah, kind of what Jeremy showed already, those single laser tracks came from a study that we did with Colorado School of Mines, namely through their Center for Advanced Non-Ferrous Structural Alloys, which is an NSF funded research center. So this is actually work that I actually got to work on. And what we did is we wanted to do a study looking at how laser powder bed fusion solidification conditions particularly impacted these industrial relevant aluminum alloys. So we took a base of 6061 with 6061 powder, as well as a material that was a base of RA 6061 M2, just a build, and then a layer of powder. So and we did some in situ work with these. So starting with the schematic on the left, basically how this experiment operated is we took a sample of a base plate and a layer of powder. And if you look at that pop-out window, you can kind of see a better picture of this. And that powder bed layer was actually set by 2 glassy carbon slides put on either side of the sample. We then put this in a chamber that was backfilled with argon, so it simulated kind of what you might expect in an actual printer. And then we had a programmable laser that we could do single rasters with, where we could set our laser power and our laser speed. And then we shot basically high energy X-rays through this material to get a series of images like you're seeing on the right. And this is a series of images that formed a radiographic, series of radiographic images that formed a movie. And you can see the actual melt pool as it moves along through that laser raster, as well as some other phenomena. But what we really wanted to track was the solidification velocity by tracking the solid-liquid interface of that melt pool. And this was because, as Jeremy already noted, we know that our solidification morphology, and therefore our microstructure of our final part, is determined by our solidification conditions. So by, comparing that to our microstructure, we know exactly how our alloys might respond given a certain solidification condition or laser parameter. So again, just showing those microstructures that Jeremy kind of walked through a little bit. We looked at, again, a 6061 M2 sample, as well as a base, just 6061 ROT sample. So the RAM2 is on the right, or on the left, the 6061 is on the right. And what we saw for each sample for each of these materials is kind of the microstructures you see here. This would be representative of the different all of our samples for different laser parameters, where for 6061, regardless of our different laser parameters, we saw that columnar growth and cracking particularly. Whereas in 6061 and 2, we saw refinement down to about 2 microns in grain size for area. And you can see also that I've marked our max melt pool depth and in our SEM image, because we actually couldn't see where our melt pool ended and where the base plate of the build began. And so the only way we could ensure that we were actually capturing the bottom of the melt pool is by considering the maximum length it might actually have. So this was just kind of an interesting study where we saw that using these inoculants, we can get refinement regardless of laser parameter conditions for what we studied for laser powder bed fusion. So not only do these particles that we're adding, our RAM constituents, actually prevent hot tearing, they also make our materials composites. So a composite is basically a material made of two or more constituents. For those of you who may not be familiar with composites, the reason that we use these materials is that you can get the benefit of both of the constituents. So say you have a hard material and a soft material, we can make a material that takes advantage of both the properties of the hard material and the soft material, the amount of which depends on the fractions of both materials you use in your composite. So just as an example, for those of you who aren't familiar with composites, some common composites would be concrete or wood. Other examples might be things like carbon fiber or glass ceramic stovetops, tungsten carbide. So we use composites very commonly in everyday life. For our materials, we're working with metal matrix composites, which basically combine a continuous metallic matrix phase with a ceramic reinforcement phase. So in this case, we get the combination of both metallic properties, which would be a ductility and a toughness, as well as our ceramic properties, which would be a high strength or high modulus. And an example of this kind of microstructure is shown in the top right, where you can see those the particles that are distributed throughout a matrix phase of a metal. And the reason we use these is that our properties actually can outperform metals for a lot of given applications. So you can kind of see two examples of this in this slide. First, in the bottom right, you can see how we can get a higher specific strength for our operating temperature for different metal matrix composites versus just their base material. We have also seen a few other properties that we can take advantage of with these materials, which are listed in the table on the bottom here. Namely, we can increase our strength or specific stiffness. We can increase hardness, high temperature performance, even vibrational dampening. So a lot of benefits to using these materials. So taking a peek at our materials, if you recall, Jeremy showed an image of a tensile bar for an aluminum material, namely 6061, where you could see those kind of fibery grains when we looked at the fracture surface of our tensile bar, indicating that columnar structure. In this image I'm showing you on the right, you can see another tensile bar that was printed with our aluminum 2024 RAM 10% composite. And you'll notice that instead of that kind of fibery surface, we now have a pretty dimpled surface. So we can see already that our mechanical behavior is different. And if we look at the microstructure next to this image, you can see all of those different particles in our metallic matrix. So for this material, we have bimodal reinforcements. We have things on the scale of microns, and we also have our inoculant phases, which are on the nanometer scale. And for this material, we get a high strength of 81 KSI, a high stiffness of 98 GPa, and we also see good wear resistance, all because this is a composite material. And we also have that additional strengthening of the equiaxed grains from the inoculant phase that forms. One other thing that we found with these composites can also show a high specific stiffness, which has currently been limited to aluminum beryllium alloys, which are kind of a problem because these can cause a lot of health issues for those that are working with them. So aluminum metal matrix composites could be a good replacement candidate. And you can kind of see an example of this on the bottom figure there, where you can see a plot of our Young's modulus versus the density of our material. And you can see a lot of different materials, namely metals, plotted there. But you can also see that one of our composites, an A1000 RAM 15, so that's 15% of our, by volume of our particles added to a base A1000 alloy, that we actually match up with Supreme 620XF, which is an alloy that's used for these high stiffness applications. So that's another thing we can use these composites for. We've worked with many different alloys, which you can see on the left. This is a spider chart showing our different properties for different aluminum alloys. But what I want you to note there is we've worked with commercially pure aluminum, we've worked with 2024, 6061, lots of different aluminum alloys. And so I just kind of want to break down what these designations actually mean for those of you who may not know. So looking at the table on the left, For aluminums, our alloy series are considered different 1,000 series alloys, so 1,000, 2,000, 3,000, so on. And each of these 1,000 series basically indicate what alloying elements are in these materials. And you can see that listed in the second column. So for instance, for our 2,000 series, we're mainly alloying with copper, and different alloys in that series will have different amounts of that alloying element. And for each of these elements, there are different benefits for each of these alloy series, but one of the benefits is that we can actually heat treat our materials to get a higher strength. So you can see for a few of those that they're actually heat treatable alloys, and that's why we want to use them, is to get better properties out of our materials. So to take a step back and talk about why we actually perform heat treatment on these materials, the reason we do this is because we can take advantage of something called precipitation strengthening. So starting with the red figure you see on the right, this is a phase diagram. This is what we use to predict our microstructure or phase development in our materials. So you can see that alpha would be our solid aluminum, our primary phase for these alloys. We have an alpha and theta region. That would be two phases where we can form precipitates or particles in our material. And then above that, we have our liquidus regions. So starting at point 1, we can take our alloy of a given composition. In this case, this is an aluminum copper alloy that's around 4%. We can heat that up to our alpha aluminum phase field so that we actually only have alpha in our microstructure. And so all of our solute atoms, all of our copper is contained within that microstructure. And this is called a solution treatment. We then quench that to freeze that microstructure so that we only have alpha phase. And then we then go to step 3, which is an age, where we go back up to a slightly elevated temperature to start to form that theta phase, which precipitates or forms small particles that then add strength to our material. And the size and amount of these particles depends on our temperature that we age at and how long we age for. So if you look at the figure on the left, looking at a variety of different aluminum copper alloys aged at different times and temperatures, this is showing you hardness versus aging time. So you can see that for the top figure, if we change our composition, we can change our aging behavior. We can get different hardnesses, potentially higher hardnesses, and we can use different aging times. And then if you look at the figure on the bottom, again, for different compositions, you see kind of a similar thing. However, this is now aged at 190 degrees C, whereas the top is aged at 130 degrees C. So if we change our temperature, if we change our time, if we change our composition, we can get different properties. So if we consider two kind of different alloys, on the top we have our 2024 alloys, where we've compared ROT, our RAM2, and our RAM10, and on the bottom we have the same thing for 6061. And what you'll notice is for ROT alloys and for our RAM2, we use a heat treatment to get our final properties. This heat treatment is known as a T6 heat treatment. And you can see with that heat treatment, we now get comparable properties, and we get those higher strengths that we want out of this material. And same thing for 6061 on the bottom. Again, that ROT and the RAM2 properties are very similar, and that T6 heat treatment is helping increase the properties for both of those alloys. The other thing I want to point out is that we also have our RAM10 alloys next to these. And what you can see is that as we increase our fraction of RAM content, we have higher strength from that composite behavior. So you can see both the heat treatment and the composite behavior increasing our strength in these materials. Finally, we know for additive, a big concern is fatigue. So we've done some research into how our alloys behave in fatigue testing. So looking first at our A1000 RAM10, so this has a higher composite content, you can see that our alloy compares well to ALSI10 and G, a common alloy used in 3D printing for fatigue. And then if we look at our A6061 RAM alloy, we can see that it compares really well with 6061 T6, which is just the raw alloy. So we've seen good performance with these composites for fatigue as well. Finally, I'm going to go over just a really brief case study. 3D Systems is going to go into some really interesting detail on this in a moment, but one case study that we did was with a 2024 Ram 10 component. Namely, we looked at a piston head. So the reason this material is good for this application is it's a lightweight material, and then we can also design for reduced inertial forces using AM. We can get some really complex geometry that helps with this application. We also see reduced coefficient of thermal expansion, and then we also saw low coefficient of friction from our metal matrix composite material. So we saw high performance and good fuel efficiency, and then also this material got good strength and fatigue life at a temperature for a long life. So if you look at the figures on the bottom, we can see starting from the left that this material behaved, had a higher yield strength than comparison to a cast or forged alloy. If you look in the middle, we can also see that we reduce the friction force with this part. So with that, I will hand it over to 3D Systems.
You just get the screen share working here. Alrighty, you should be able to see my slide now. Let me know if you can't. Thanks, Chloe and Jeremy, for that. For those first two presentations. I've definitely learned something. It's some really cool, deeply technical content. My name is Aaron Schmitz. I am a process and validation engineer with 3D Systems, and I'm joined today by Dustin Kraus, a colleague of mine who's a senior application development engineer. And we're mostly going to be focusing on a little bit of an introduction to 3D Systems as a whole, but mostly our experiences in working with A6061 Ram 2 from Elementum 3D. So I'm going to start off by giving us a brief introduction to 3D Systems as a whole. I'll talk about our application innovation group and its purpose, which is the group that Dustin and I work in. I'll talk a little bit about our initial experiences in developing aluminum 6061 Ram 2 on our systems. And then I'll let Dustin take it over where he'll dive into some cool applications we've been working on with customers and where we see the future of aluminum powder bed fusion of metals. So this is our overview slide on 3D Systems as a whole. And if there was sort of one takeaway I had for everybody, it's that in the additive industry, we probably have the widest breadth of offerings in terms of technologies and softwares of anybody. So today we're mostly focusing on direct metal printing, as we call it, or laser powder bed fusion of metals. We do that, and we have multiple different platforms we do that on. We also do a lot with plastics. So we are in stereolithography of plastics, selective laser sintering, FDM, all these types of things. So we really offer a wide breadth of material technologies. And we also support not only the hardware that those materials get printed on, but the software to prepare builds, the software to run those machines, and services to go along with it all. Looking back on the history of 3D Systems just a tiny bit, we were founded in the 80s by Chuck Hull, who is actually credited with inventing 3D printing, depending on who you talk to. So it's pretty cool. He still works at 3D Systems and is in a technical role, not just an advisory role, working on some bioprinting we're working on, which is cool. And then looking to the future, one cool thing we're working on is what is proposed to be the world's largest and fastest metal additive machine under a contract with the Army, which will be really cool. The group that Dustin and I work in is the Applications Innovation Group. We are over 70 employees strong and essentially service the entire globe. And what the Application Innovation Group is really focused on is across all those different modalities I said 3D Systems offers in terms of printing technology. So direct metal printing, selective laser sintering, stereolithography, etc. We cover all those different technologies across all applicable industries, essentially. So on the right, you can see all the different industries we focus on. Historically, we've done a lot of healthcare applications, so we're really good at printing spinal implants and things like titanium and things like that. But we're moving more and more into the industrial space, which is actually where aluminum 6061 is primarily coming in industries like semiconductor manufacturing, the energy industry, aerospace and defense, etc. So we primarily exist in the United States, in Colorado and in Belgium, but we support customers across the entire globe in over 68 countries, which is pretty cool. In a little more detail, so as I mentioned before, you see on the right, 3D Systems not only covers machine technologies, but the software to run those machines, the preparation software to prepare builds on those machines, as well as unique materials and application support. So something I didn't actually mention, this is primarily on the plastic side, but 3D Systems self-funds and does a lot of materials development, not just of parameters to print materials, but in plastics, we actually do a lot of our own polymer development, which is kind of cool. On the metal side, most metals are not proprietary, but we do develop parameters for all those metals ourselves on our systems. So the Application Innovation Group offers a wide variety of services. So we offer trainings across all those platforms. We teach people about additive manufacturing if they don't know much, and we actually cover the full product lifecycle, which is cool. So we do consulting work with customers to stand up entire processes to make parts. We don't just sell machines and teach people how to print a part, but we do things like cleaning validations, post-processing validations, and things like that, and get people set up really end to end. One cool service we offer is custom material development. And when I say that, what I mostly mean is parameter development on our systems to print materials. So if a customer is used to working with a certain alloy subtractively, let's say traditionally, and they want to seek to 3D print that alloy, as long as we can source the powder for it, we offer a service where we'll develop the laser parameters to print that material on our systems. And in some cases, as you can imagine, there are certain alloys that apply across a wide variety of industries, have a lot of different applications and potential customers. And in those cases, we'll decide to develop that alloy ourselves in-house, self-fund. And that's what we're doing with aluminum 6061 right now. So in development of aluminum 6061 RAM 2 from Elementum, this is the system we primarily focused our development on initially. It is our mid-frame direct metal printing machine, the DMP Flex 350. It also, as you see on the right, has a quote factory upgrade, which pretty much just adds closed loop powder handling. This is our mid-frame system, so we do have smaller laser powder bed fusion systems as well, Flex 100 and 200. Those do smaller components, things more like dental applications and things. But we also have a large format machine, which is 500 by 500 by 500 millimeter build volume. It's a 3 laser system meant for much larger industrial applications. A little more on the Flex 350 itself. There's really 2 things I would hit on that are a little unique about it. One is our sort of quick swap build module system. So the entire build platform with the build volume where the platform syncs, and then the feeds that raise up to recoat powder across. All of this, including the recoat system and everything, is in a module that can be slid out of the machine. And if you have a second module, it can be slid directly in, which basically creates a incredibly quick flip time on the machine if you're trying to do high productivity manufacturing in additive, which is cool. And the other thing that's somewhat unique is our vacuum chamber concept. So the build volume itself is actually built like a reverse pressure vessel. So to inert the weld environment, we pull vacuum and suck all the atmosphere out of the build volume, and then we backfill it with argon. And then we suck all that argon out and backfill again. We do that process actually 3 times, which yields a best-in-class oxygen or best-in-class purity overall for the weld environment, with oxygen purity typically being below 25 parts per million. And that just leads to really good process stability, especially in alloys like titanium, where you get a lot of powder oxidation and things like that. If you're not careful, you can use your powder over a long period of time without it oxidizing too quickly. It's a really safe environment for the powder to be in and to be welding in. So our initial experiences in working with a 6061 RAM 2. So not a ton of technical details in terms of numbers and strength and properties and productivity and things like that on here. If you're at all interested in that, definitely just reach out to Dustin and I, and we can give you all the details on productivity and things like that with this alloy. But this is more of just our experiences in working with it initially, and then Dustin's going to dive into applications. So starting sort of from scratch on parameters, we very quickly achieved a fully dense infill. We found the alloy to be pretty easy to work with. Can everybody still see my screen just fine? Something weird popped up. I'll keep going. Let me know if you can't. We very quickly achieved a fully dense infill with an optical pixel density method, fast recoat speed because we found the powder to be very flowable, and then across our portfolio of metals on this system, we very quickly found it to be the most productive alloy we offer and about tied for the best as printed surface finish. So we found it to be easy to print with in general. And then just comparing it to traditional aluminum alloy of ours, aluminum silicon 10 magnesium, which Elementum 3D already talked about a little bit. The surface finish is significantly better, at least 50% better, as you can see on the bottom right. The productivity is better. The ductility and strength are both better, and the thermal conductivity is the only thing that is slightly reduced from aluminum silicon 10 magnesium, but it being an aluminum alloy, it's still way better than your typical steels and titanium, so still really great for heat transfer applications. And with that, I'll hand it over to Dustin so we can talk about applications a little more specifically.
So yeah, 3D Systems, we've actually been printing with A6061 RAM 2 for a couple years now, and this is just our time to come out of the woodworks and show some really neat applications. So here I'm going to cover 4 different applications, each of which covers a different, highlights different properties that are really interesting for this material. So the first one is a space application wherein we worked with a South Australian company called Fleet Space. They had a couple years ago actually already sent up a few satellites, their own constellation called Centauri, and based on that experience, they are developing a new constellation of 140 satellites called Alpha. And this is said to be the first completely 3D printed constellation of satellites, and they're going to start sending these up in the next 12 months. The purpose behind this product is communication. It's going to be a low Earth orbit satellite to assist in the global coverage of the internet, the IoT, Internet of Things, 5G, and just connect the world, kind of like SpaceX's or Elon's Starlink program. And where we came in was developing and moving from prototyping to small batch production of their patch antenna. It's the square thing in the orange box there on the right that you can see. So these patch antennae are actually on the exterior of the satellite. They're placed in a grid array, and they're actually going to be taking and receiving signals from the Earth. And so, like I said, this constellation is intended to be 140 satellites, and on each satellite, that's 64 patches. So that's several hundred patches, and normally building these kinds of patches would require 10 to 20 manufacturing operations, and your lead time would be minimum 12 months, where in this case, using laser powder bed fusion and A6061 RAM 2 in particular, we were able to go from prototyping all the way through small batch production in a matter of 3 weeks, wherein we helped with some of the design. We had to do some laser parameter iteration, and now we're actually moving to a full technology transfer to Fleet Space, who will be onboarding one of our Flux 350s to bring that production in-house. Something else that's really an interesting or a point of interest is the fact that these patches had novel cavities, internal cavities that really wouldn't be able to be machined anywhere else, and by the nature of their design, enable a novel filtering, signal processing, and signal tuning that you really wouldn't be able to get any other way. And also, this application really shows the thin wall capability of this material. I mean, you're talking less than 1 millimeter wall thickness of each and every one of these, and we were able to move from development to production very rapidly. So it's a material that has a very wide processing window and really good electrical conductivity for these kinds of bandpass filter applications. So the next application is more research oriented, still kind of on the space realm. This is the EXCITE balloon-borne mission. This was in collaboration with NASA's Goddard Space Flight Center, where they generatively designed a structural bracket to holds some of the equipment for a balloon-borne telescope. So kind of what you're seeing here in the middle, this is the balloon. Once it's inflated, it's a football field size or football stadium size balloon. And then you got this tiny satellite there at the very bottom that actually has the telescope and the payload and everything. And in the orange box here, the organic looking bracket there, this is what we're talking about right now. This is the generatively designed bracket that 3D Systems produced in both ALSI-10 magnesium and A6061 RAM2. And so the mission of Excite is to study the atmospheres of several exoplanets. I mean, we know of lots of exoplanets. We actually don't have much data behind how their atmosphere changes around their orbits. So using a balloon-borne telescope such as this enables us to track the orbit and the atmospheric fluctuation over the course of several months. However, the drawback of using that is that when you're in such a high atmosphere, you're subjecting your equipment to large, very harsh wind conditions, vibrations, and very cold temperatures, all which can lead to brittle fracture. So NASA decided to go through quite a bit of testing using different materials, different machining operations, different manufacturing operations. And so we were proud to say that we passed with flying colors for this part. With all our in-situ monitoring data and CT mapping and NASA data, they showed they really couldn't find really any defects at all. They've done vibration testing and again, passed with flying colors, and they've also run several FEA models and have shown that using the generative design equalizes the strain over the part, reducing stress concentrations, which essentially means that your stiffness and your mass to weight ratio leads to a 5 times improvement in strength and just general performance, which is huge for these kinds of applications. So real quick, we'll move on to well, the next two are more about thermal performance, thermal cooling. So we've actually printed and tested some parts with a well-known motorsports company in a harsh saltwater environment. This application is for thermal management of some of their hydraulic motors. Again, we were able to very quickly use this material to help them in the design and the printing, and they could actually get it installed and tested on an actual race. And some interesting points, again, is how easily this material anodizes, and that can sometimes be an issue with some of your traditional LPBF aluminum alloys like ALSI-7, ALSI-10. Sometimes they don't anodize that well, and you have to go through a couple surface treatments to get it to anodize well. But these anodize very readily and have been tested in harsh saltwater conditions and have proven to stand up. Also, the team that we've worked with has shown a proven reduction in their operating temperature and better thermal management on the order of 20-25%, which means that they can go faster, harder, stronger, all that kind of good stuff. Same thing with the RF patch or the patch antenna, internal cavities that would be very difficult to machine, and part consolidation, as is typical with the advantage of using additive manufacturing with heat sinks. You can why take 20 to 50 operations to assemble your heat sinks when you just print it all in one go. And the last application is for the semiconductor industry. It is a silicone wafer table. This was actually featured on last summer's front cover of the Metal AM magazine. So this actually was built in A6061, again, pointing to the fact we've been printing this for a while, just under the radar. So in terms of these silicone wafer tables, thermal management is critical. The faster and more uniformly that you can cool cool your wafer will drastically improve your productivity. And so optimizing the fluid flow within the wafer table itself, as in all the negative empty spaces, all the negative cavities that you can see in here, is extremely important. And what we've seen with A6061 is that it has great as-built surface finish. So you would not be able to get in and do some kind of post-surface finish improvement after the fact with this kind of part. So A6061's as-built surface finish being as good as it is actually has proven to result in a 90% reduction in disturbance forces, which actually can lead to improved accuracy for the chips themselves and an overall better thermal management. I think in this case study, we saw a 50 times reduction in cooling times, six times improvement in thermal performance, and just generally all around lots. This is a great application for both this material and laser powder bed fusion. And lastly, what does 3D Systems think about high strength aluminum such as this for the future? Well, we are going to continue to develop our data set for A6061, the Flux 350, building out the validation strategy, further optimizing parameters, just really and looking for partnerships to develop more applications. As the semiconductor industry has seen the advantage of using laser powder bed fusion with the breakdown of the process of the supply chain, we are seeing much more demand for large platform aluminum parts. So we're going to look into developing high strength aluminum on our DP Factor 500 3-laser system. And with that, I think I'm the last one. So we'll open up to questions.
Thanks, Dustin. Our first question is there an option to print a solid aluminum part with no internal lattice? The attendee design.
I think you cut out there at the end, Chloe. But can you build a solid aluminum part without lattice? I mean, yes, we've kind of shown it here for the other applications, and 2 of these applications were all about thermal management. So yeah, this probably could be a good solution for whoever asked the question.
Perfect,
Yeah.
thank you. Can you touch a little more on thermal transfer?
Yeah, we're still gathering the data on the thermal conductivity of the solid material. We've already performed the electrical conductivity and some of the other mechanical measurements. So I would say, like, I don't have hard numbers, but as a comparison, this performs just as well, and I would argue better than some of our other aluminum alloys, such as AlSi 7 and AlSi 10. So you could just go reference AlSi 10 thermal conductivity, and very likely, and maybe the Elementum guys can weigh in on this, this will perform just as good, if not better.
Thank you. Next question is, are these material parameter databases available on all metal printers from 3D?
I've got this one, Dustin. Yeah, so right now the parameter set is not broadly available or published to everybody with 3D Systems machines. Right now, you need to contact either Dustin or myself and work through our Applications Innovation Group in Colorado. But we are making some final updates to the parameter set and developing a parameter or a materials database for the material for the material coming off of our machines. And all of that is going to be officially released and rolled out probably this fall. There's just more data gathering to be done this summer. And then if you want the opportunity to print with the parameters yourself, you do need to pay for the specific package to print in aluminum. It's not like just having a machine means you get every parameter set automatically. It's kind of on a case-by-case basis. You just pay for your module is what it's called. So reach out to Dustin or I if you're interested in working with the material on 3D Systems machines in the near term. And this fall, it will be commercially available.
Perfect, thank you. Next question, are there any projects that have been done with bi-material LDPF and AL6061 yet?
From the 3D systems side, no. I don't know, Jeremy, have they done any kind of cladding with elements in 3D?
Certainly things like anodizing that we touched on, things like that, surface treatments have been done, and I think welding has been done as well, traditional welding to other materials, but not fully additive by metal materials.
Thank you. Our next question is for Elementum 3D specifically. Are you looking into further optimized heat treatments other than T6 for A6061?
Yeah, we have studied a number of different heat treatments there, but we've found that for most customers, the T6 heat treatment is the preferred balance of both strength and ductility. But certainly other heat treatment options are available. And in general, the heat treatments that you can do on a wrought 6061 alloy will also work on the additive 6061 RAM2 alloy.
Thank you. Our next question is, can you compare the recyclability of this material to metals-only alloys?
Yeah, we've done a number of recyclability studies or reuse studies, as I would call them, and where the powder can be reused a large number of times. We've done several different studies, including where we collect properties both of the powder and the parts after printing a number of times.
The next question is, are any of these aluminum materials recognized as food safe?
That's not an area I have experience in. So great question. If anyone else has any knowledge there, feel free to chime in.
Yeah, it's nothing that we've studied at this point.
Okay, that's something that we can check in and reach out directly to you on. Do you see potential for adding higher strength aluminum alloys in addition to 6061 RAM2?
Yeah, definitely. That's something we're constantly working on, is new alloy development. And actually the gambit of materials we've worked with is constantly increasing. So even some of the things that I showed today are not our limits on what we're researching and what we'd like to do in the future. So definitely reach out if you have a specific need or property or alloy. We're definitely always in development.
Thanks, Chloe. Can you design alloys with properties targeted for specific applications?
Yes, definitely. And this is one of the things that the RAM technology really is well suited for. By controlling the amount of RAM additions to a given base alloy, we can tailor the properties that the customer needs for the application, including strength, stiffness or modulus, and other elevated temperature performance, wear resistance, all of that. So we can very easily control that with the amount of RAM additions, as well as through selection of the base alloy.
Great, thank you. Our next question is, how does build productivity look versus other materials so far?
So relative to our laser form ALSI 10 on the Flex 350, 6061, it's probably like a 5 to 10% increase in productivity, but by no means is our parameter set optimized at this point. And that's actually going to be the next coming months, is specifically to improve that productivity. In fact, Aaron ran a couple productivity DOEs yesterday. Again, the as-built surface finish of 6061 is far better than any of our other aluminum materials, which is a big win. So we certainly expect that by the time we're fully optimized, that 6061 will have markedly better productivity and surface finish, in addition to slightly better mechanical properties as well.
Great, thank you. Next question is, does 6061 experience any marked increase in properties from hot isostatic pressing?
Now, for certain customers, certainly HIP is the preferred method, and we do have customers that are doing HIP to the material. We don't really find a big increase in strength or anything like that, and we haven't fully studied fatigue in the hipped condition. So I think fatigue would be the interesting one to look at there. We get great fatigue performance without the hip, but perhaps it's even better with the hip. We're not sure yet.
Great, thank you. Are these high-strength aluminum alloys available in large quantities?
Yes, we can produce large quantities today, so they're available today in large quantities.
Thank you. What kind of surface roughness are you seeing as built and with finishing?
I could maybe just hit that for 3D systems, and then if Jeremy or Chloe has more data from Elementum. So already with our non-optimized process that we're improving, like Dustin said, we have 8 micron RA on vertical surfaces, which is quite good for an additive process.
Just to add to that, what sort of finished surface that can be achieved? We have some partners we've worked with on the finishing side that have been able to achieve mirror surface finishes, so very, very high, very low roughness surfaces, and it'd be really mirror finish.
Great, thank you. What is the powder suffer? Does the RAM powder suffer from any losses of the RAM additions during the re-sieving powder process?
Yeah, this is maybe related to the previous question, and I think we've definitely reused powder mini cycles through sieving. One of the studies we did, we actually specifically focused on that question, and so we designed a sieving method where we could collect the powder in the order that it exited the sieve. So we put the powder in the sieve, collected the powder that went first through the sieve at the bottom of the container, and then we used that container with a bottom feed method. So the powder that first went through the sieve, we fed that into the sieve first. So we were doing as much as we could to stratify the powder. We did that 15 times, passed it through the sieve, stuff that went through the sieve first, put it in the sieve first. And then we printed with the powder separated based on the order that it sieved. So the stuff that sieved first after 15 cycles and the stuff that sieved slowest after 15 cycles, printed parts, looked at the powder, and we found that those parts, the printed parts, still had very consistent properties, whether it was the material that went through the sieve first or the material that went through the sieve last after 15 cycles, intentionally trying to stratify it. Yeah, there is a white paper out on this study as well that you can access through our website.
Thanks, Jeremy. Our next question is, do high-strength aluminum print slower than other aluminum alloys on the market?
And yeah, that's a bit of a broad question, but I would say in general for the high strength alloys we're talking about here today with the RAM alloys, no, they actually can print faster. And that's a combination of the base alloy selection, but the RAM additions actually do add a little bit of energy to the process, so those can help. And as well as they provide control of the viscosity of the melt pool and control of the solidification. So because of that, we have a very wide processing window and can actually increase print speeds over many traditional lower strength aluminum alloys.
Great, thank you. We have time for one more question. What benefits does this alloy have over the current aluminums that we offer?
Yeah, I could probably take that one. So what 3D Systems currently offers is scalmalloy. It's a scandium alloyed aluminum, AL size 7 magnesium, and AL size 10 magnesium as well. So what we've seen is that 6061 RAM2, again, not only flows better, which can improve our deposition times, which can ultimately lead to higher productivity, but also, like I mentioned previously, can anodize more easily, better as well surface finish. You don't have the scandium or the silicon from the other alloys, or as much silicon that can cause issue for other post-processing like chemical etchants, chemical etching treatments. And generally speaking, I think the A6061 RAM2 is slightly cheaper than scalmalloy while having nearly as good mechanical properties.
And to add to that a little bit, I think one of the other advantages is that it's closer to the traditional alloys that people are familiar with. People widely use 6061 wrought alloy. And so while this is a 3D printed material, and so there are differences and there are some compositional differences as well, the performance is very close to the wrought alloy that people may already be familiar with. And also because it is based on a traditional wrought alloy composition,